Might wait a couple minutes as people start trickling in.
Let's replace B and C with A's all throughout. That means that, so now we have A implies A in the conclusion, like we want. And now we have this part. So if we can write something that looks like this, then we can get the conclusion we want. And this almost looks familiar. It almost looks like something that could be made from K, except it's not quite, right? Because K is like this. And so if you tried to like match these two together, you would get that this has to match with this, so that B would have to be A, and so that this would have to be A, and then these don't match, so you can't directly plug it in. So now we have to do something more clever than that, it turns out. It's not entirely straightforward, but the idea is that we are going to just change C to be A. And then we are going to change we're going to change B, I think. And then we're going to change it to be A implies A. And now we're in parenthesis hell, but if we keep trudging on, we'll see that this part finally looks like the conclusion we want with K. If we replaced A with A implies A, then how do we get this part? Oh, wait. That's not right. Give me a second to think about how to do this, because it turns out to be slightly more complicated than I thought it would be. I mean, like I expected, I guess. Okay, so yes, so we took S and then we gave it this. We're gonna take this first K, and then we're going to replace B with A implies A. And then we're going to take K again. We have this. And so we're going to apply modus ponens twice in order to get, so this first part matches this one, and this second part matches this one, right? Okay, so my mistake was that I gave the wrong axioms, and the actual correct one is this one. Okay. I don't think that affects too much. All right, so now we can write our full proof, and it looks like this. So we have here, so this follows from S, and then we know that this follows from K. So let's write A implies A implies A implies A. So this follows from K. So from modus ponens, we can conclude this part. And so we're missing parentheses. And then we once again use K. So use K like this. And then we again use modus ponens. And then finally we end up with the conclusion we wanted, A implies A. So the whole point of this is that like we can prove theorems like A implies A. And in fact, it is in fact the case that we can prove like, you know, everything that seems like it could be a true theorem of logic, but just implies, we are able to just prove using combinations of K, S, and MP. But as we've seen here, it turns out that the method for doing so is a bit complicated, and remembering how to do it is also even more complicated. And it's not easy, but it is possible. In fact, we could also try proving even harder statements like, let's say we wanted to prove that A implies B, implies that B implies C, implies A implies C. Which is kind of like this transitivity kind of thing happening where like show A implies B, then if B implies C, then A implies C, because A implies C. If A was true, then it would imply B was true. B was true, C was true, so therefore A would imply C. And then given that A implies A alone was already very hard, it turns out that the proof of this is actually even harder. And I can at least remember the first step. And the first step involves taking S. And then you want to replace A with B implies C, and then you want to replace B with A implies B implies C, and you want to replace C with A implies B implies A implies C, and then you plug it all in, and that's just the first step. And then there are several other steps after that, and the proof is like complicated but possible. So that we're just going to write that. All right. Any questions about the logic things we've been setting up so far? Okay. We will once again have another convention. Another important convention. And that is implies is right associative. So instead of saying A implies B implies C, we can just write this as A implies B implies C. And so now we can write our rules K and S in a shorter form because they are right associative. We can just say that we can get rid of these parentheses. We can get rid of these parentheses. Get rid of these parentheses and these parentheses. So now our parentheses are now gone, and we have cleaner rules just because we say that implies is right associative. But yeah, great. So at this point, you may be wondering two different things. One, why did I talk about logic in a type theory lecture? And two, what is up with me using the same right arrow for both the two, like the function type in type theory and the implies in logic? And not only that, but we're also saying that they're both right associative, and we've been doing kind of similar manipulations with them even. And to explain the connection, we're going back to type theory, and we're going to talk about type inference. And for type inference, what we're going to do is we're going to write an expression, and then given this expression, we're going to try to determine the types of everything. So for example, let's say we had some function f, and then we plugged in pi, and then we get the result of 3. And let's say we knew that this pi was real and that this 3 was int. So what is the type of f? Anyone? So the type of f is real to int, because it takes in a real number and returns an integer. All right, so let's go even further. Let's say we saw the expression f of pi. And that's it. We don't know what it is equal to. Well, we could say that like f has the type real to A, then we're just going to say for some type A. We don't know what this type A is at all, but we can at least say that F takes in a real number. It takes in some real thing. And in fact, for any type F, right? Like even if we don't know anything about it, we know already that it has type A to B. For some types A and B. And this might seem like an almost useless statement, but it's in fact like quite deep, because the fact that we're saying that it has this 2 type is already telling us that it is a function. We know that its input is of one type and its output is of another type. And this is all just from the fact that we know that this is a function. And so this is actually like somewhat okay. Maybe an example will help. Let's say we have a function that takes any x and then it returns like a negative x. And we will call this function neg for negate. So what is the type of neg? And then you're going to ask me, well, do we know that x is a real number, or do we know that it's an integer? You could say that neg has type real to real, or it could be type int to int, or it could even be type like complex to complex, or whatever. But in general, right, you can say that neg will have type A to A, and this will be true for some type A. So let's look at this other function. Let's do some more type inference. So this function will be called apply. And apply will take in some y, we don't know its type, and it will take in some z, we don't know its type, and then it will return y applied to z. So what is its type? Let's say that z, so let's just start assigning types to things, right? So let's say that z has type A, or some type A. We don't know what type A is, but we do know that it's going to have some type A. So we know that z has type A, and that we're applying y to z, which means what can we say about the type of y? We know that y has to be a function, right? And we know not only that, but we know that its input has type A, and its output, we don't know anything about its output. Let's just say its output is type B. So now we know that the type of y is A to B. And given this information, we can say that the type of apply is A to B to A to B. So it takes in A to B, y, which is a function that goes from type A to type B. It takes in z, which is something of type A, and then it returns y applied to z, and the result will be of type B. So you can imagine, for example, writing apply, like say, neg to 3. And so we saw that neg had type int to int, or it had type A to A. And we saw that 3 had type int. And we know that apply has type this one. And we know that these aren't necessarily the same A, so let's change this A to alpha, just to be clear. So when we write apply neg 3, so first, this input of apply, which is A to B, must match the first input, A to A. And so we get that A has to be alpha and B has to be alpha. So that means that the type of apply neg will be alpha to alpha, because it has to be this type, and then we know that A and B are both alpha because that's the input type. And so because this is type int, and this function has type alpha to alpha, that means alpha will be int, and that means the whole result will be int. And indeed, we can check this. So here, we're only talking about the types. We're not like thinking about the internals of the functions at all, but we can think about the internals of functions. So let's write out apply. Apply is the function y maps to z, maps to y applied to z. Neg is the function x maps to minus x, and then 3. And then so we first apply this one to this input. And so the result will be, so this one will have to be y. So that means that the result will be, we take this and then we replace this part with this part. The result will be z to x to negative x applied to z. And then this function is applied to 3. So because it's applied to 3, we're replacing z with 3. And so this is going to be x to negative x applied to 3. And this is a function application where we're replacing x with 3. So the result will be negative 3, which is indeed an integer, just like we expected from the types. So once again, here on the left, we aren't doing any, we're not actually computing what its value is. We're just looking at what its type could be. And knowing the types of everything allows us to predict that its type will be integer. And so when we actually evaluate it, we can see that it does have the type integer. And so we're right. Okay, are there any questions about these examples on type inference? So let's move on. I'm going to define 2 functions that will look familiar. So the first one I'm going to call k. And I'm going to call this function k because it is a constant function. It takes in any x, and then it takes in any y, and then it returns x. So it is constant because no matter what y you plug in, we always return x. So that's why it's called k, because k is for constant. What is the type of k? Well, it could be a, because x could be anything. Y could be anything, and then it returns x, which we know has type A. I'm going to define another function, which I will call s, and it will be called s for substitution. So s will take in x, and then it will take in y, and then it will take in z, and then it will return x applied to z, applied to y applied to z. And so you're kind of like substituting z in for x and y, and that's why we're calling it s for substitution. What is the type of s? Well, it's a bit more complicated because we're applying things to things. So we can't just say A to B to C to something, because you can't apply like say A, you can't like have this be B and this be A. So let's do the same type inference process that we did with apply. Let's say Z has the type A, because it could be anything. And this output, it could also be anything. It's currently not restricted. So let's say this has type B. And that means that Y will have type A to B because it takes in A and outputs B. And so we now know that this big thing has to be some type, like let's say C. which means that this function, the one that you get from applying x to z, has to be of the type it takes in a b, and then it returns c. And so because z has type A, we know that the type of x has to be A, returns B to C. And from this type inference, we can now write out the entire type of S, which is the type of X, which we saw is A to B to C. And then the type of Y, which we saw is A to B. And then the type of Z, which is A, and then the return type, which is C. And so we have these two functions, K, constant, and S, substitution. And we've written out their types as A to B to A, and A to B to C, A to B, A to C. Does this look familiar?
Yes.
Wow, it does. In fact, it looks just like the K and S axioms that we wrote out earlier, right? And this isn't just a coincidence. In fact, do you remember what we did when we tried to prove that A implies A using just these two rules, K and S? In fact, we can try to evaluate the type of something, and I'll show you something magical. Here. So let's consider. Consider the expression S, and then you plug in the function K. So the question is, what is its type? Well, again, we're not evaluating it, we're just looking at the types. So we know that S has this type. Then we're plugging in K, which has this type. So that this has to match with this. For the sake of clarity, let's say that the type of K is instead alpha to beta to alpha. And so when we apply S to K, we need to change all of the alphas to A's to alpha, B's to beta, and C's to alpha. And so that means that the type of S applied to K has to be this one. So alpha to beta, and then takes alpha, and then returns alpha. Again, we're not evaluating SK yet. We're just writing out its type. And so next question is, what about SK applied to K? So here we have SK. And then let's write this actually in the next page. So here we have SK. And then we have K. And we know K has type A to B to A. So A to B to A. And again, the matching of the inputs must mean that alpha has to be A and beta has to be B to A. So that means that the type of the result, SKK, will be alpha to alpha or just A to A. All right? So the type is A to A. So out of something with type S and type K, we have produced something with type A to A, and it is SKK. And in fact, we can rewrite, we can evaluate it. So this is S, and this is K. And so the first thing is we plug in this for this. So that means that SK has to be, so that means that SK has to be, it takes in some, let's change these letters so that it's clearer. Like let's say this is type A to B to A. Oh, this is not type, this is mapping now. This maps A to B to A. And so SK would take Y and map it to Z and map it to A, maps to B, maps to A. applied to Z, applied to Y, applied to Z. And so we can already simplify, let's not yet. And let's evaluate this part, where for clarity, we're going to apply it again to K, which we will write as C maps to D maps to C. So this part here. That means that SKK will be Z maps to A maps to B maps to A, Z, C maps to D maps to C, Z. And so this function, this is a function that takes Z and then returns whatever this is. And so let's try to simplify this. It takes Z, and then let's evaluate this inner part. So it's taking C, and then Z would replace the C. So this is a function that takes D and returns Z. And so this one would apply to here, and so this one would just be Z. And then this would just be B returns Z. And so that means that this one would be B, which means that this whole thing would just be Z returns C. And so now SKK is just the identity function. No matter what you place in, you're going to get the same thing out. And it indeed matches the type that we predicted, which is A maps to A. And again, here we did two completely different things. In one level, we are evaluating the types. So we given this type A to B to A, and given this type A to B to C, A to B, A to C. And then we evaluate it just by looking at the types. That SKK has to have type A implies A to A. And then on another level, we are actually computing what these functions would be by substituting like K for S, and then substituting K again. And then we get that it is the identity function. And so SKK has type A to A. This is directly related to the thing we saw earlier, all the way earlier when we were back talking about logic, where we use just K and S in order to prove A implies A. So we went from just working with types to proving theorems about logic. And another example is, so you recall that thing we talked about earlier, that hard thing we said I wasn't going to go into the proof to. Well, it turns out that this has the type A imply A to B to B to C to A to C. And because this thing has the type this, and it is easy to check that this has type this, we can just use the derivation of this type in order to prove this theorem using just the axioms S and K. So this term itself, the fact that I can write this down, is already a proof. In fact, the fact that we can write SKK down is already a proof of this whole thing where we were applying S and then K and then K and whatever. This entire proof we have managed to encode with just the symbol SKK. And this is very powerful because we have gone from like a type system to a proof about logic. And this should be amazing. And this correspondence is known as the Curry-Howard correspondence, or the Curry-Howard isomorphism, depending on which source you read. And it's a very deep correspondence that forms the basis of many of today's proof assistants. So before I give a demo, are there any questions so far?
I'm new here. I'm new here. I just joined like, I don't know, 50 minutes late. So what exactly did we cover during this guest lecture?
Yeah, well, a recording is going to be up, hopefully.
Okay.
But the very brief thing that we did is that we started by talking about types and saying that, like, you know, we say things have types, we say functions have types. And then we talked about logic, and then we say, here is an axiom of logic, here are two more axioms of logic. Using these axioms of logic, we can prove theorems like A implies A, which sounds really obvious, but it turns out that proving it using just these three axioms is hard. And then we said, let's talk about type inference, and let's talk about how functions can have types, even though we don't fully know what types they are. And then we use these two magic functions, s and k, to write out a derivation that because skk has this type, we can use this to write a proof that A implies A using the system that we wrote earlier. And this thing is known as the Curry-Howard correspondence. And the TLDR is that instead of proving things, all we have to do now is worry about types. And this is how computers work with proofs. Any other questions? So for the last 5 minutes of the talk, I want to give a demonstration of how this gets applied in practice. And so this is Coq, and Coq is this proof assistant that mathematicians use in order to prove theorems about several things. And Coq has a type system that works very similarly to the one that we described. So, for example, we can say k. So k will be a function that takes in x, a type A, and y, a type B, and then it returns x. So this is the same definition for k that we wrote out earlier, this definition. And then we said that it has type A to B to A. And then, in fact, we can ask Coq what type it has. And then it indeed says that it has the type A to B to A. And so let's also try writing out S. So definition S, it takes in X, and X has type A to B to C. It takes in Y that has type A to B. It takes in Z, type A. And then we return X applied to Z, applied to Y, applied to Z. So X applied to Z, applied to Y, applied to Z. And then we can check that S has the type we expect, A to B to C, A to B, A to C. So, so we did say that SKK has this thing, and we can write SKK, and it does have the type something to something, just as we expected it to, which is supposed to be really cool. And then you remember this thing I said earlier when I said that this thing has this type? Well, let's check that. So it's SKS. Okay. It does have that type. B to C, A to B, A to C. These are just relabeled. You just have to like imagine that A and B and C were like shuffled around, but this is just the same thing as we wrote out here. So because of this, like this term alone, the fact that it has this type is already a proof that given these two axioms, K and S, we can prove that this. And this generalizes into even bigger things. So for example, the way we would write the naturals in Calc is that a natural number is either 0 or the successor of a natural number. This already exists, so let's undefine everything. And so we can check nat, so nat has type set, and then we can, so nat already gives us this induction principle, which says that for all propositions, if we prove that it's true for 0, then proving it's true for n, and then prove it's true for successor, then it's true for all n. So I'm going to write out something, and don't worry too much about what it means. So we're going to define addition on the naturals. And then if it's return A, if it's Sn, return S plus A to N, then end. So we can like check compute plus of like say S, S, O, and S, 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 O. So that's 2 plus 3. We can check it has 1, 2, 3, 4, 5 S's. And so if you could try to prove a theorem, that plus 0. The theorem says that for all A, B naturals, 0 plus A for all A naturals is equal to A. Oh, I need to write plus. And so proof. So now the way that this works is that Calc tells me a proof obligation, and then main idea is that we induct on A. Case is trivial. So this case is just reflexivity actually. And then this case is we substitute IHA. No. First we simplify, then we substitute IH, and then we rewrite IHA, and then this is reflexivity. 2D. And then now we can check plus 0. So plus 0 has this type, and then it says this is the type of the theorem that we proved. And because we proved that it has this type, the theorem is true. And the proof of the theorem is just the definition of it, which is just applying a bunch of functions to a bunch of functions. And this is like the inductive function, and this is the function that proves A equals A, and this is the function that proves something, and so on. And these are all just functions applied to functions. And the Calc says that, oh, I checked all of their types, and because all of their types is good, that means that you have successfully proved this theorem, and now you can use it for the rest of your life. And this is basically the same kind of technology that was used in used in like computer proofs of like the big 4-color theorem proof, and we expect that this technology will be used in the future. It's kind of like people are like somewhat scared about like job security as a mathematician. Maybe you're scared that like one day computers will eventually replace us, but it turns out that the state of the art for what computers can do is still at the level of like assisting, like us assisting proofs to check proofs. We don't actually let the computer come up with the proofs themselves most of the time. It is us guiding the computer in order to write out all of our proofs formally, such that the computer just looks at all of these types in the end and says, oh, these types look good, therefore this proof has to be true. And so we could rest a little safer at night knowing that the proofs of our theorems are all correct, even if not one single person has looked at every single thing and checked it, because we have computers to do that for us. And the TLDR is that like computers are cool, types are cool, we can use them to prove things. That's how they work. All right, that's it. Any questions?